Okay, I think that we will start. Good afternoon. Shortly, we'll hear an interesting lecture by Dr. Ofer Sinai on epitaxy gone and its importance both technologically and scientifically, with applications to fast-switching transistors, power electronic devices, blue to UV light source like LEDs and lasers, and display technology, tandem, photovoltaic cells, and more. This webinar is part of Enlightening series organized by Photonics Israel, exploring diverse facets within the field of photonics. Our mission is to enrich photonics knowledge, fostering collaboration not only within Israel, but also with photonics entities worldwide. Photonics Israel is sponsored by ISORAD and work in close cooperation with its subsidiary, the Israel Center for Advanced Photonics. We have a close relationship with similar clusters in the US and Europe. My name is Shlomo Glaser, and I'm the manager of Photonics Israel. Dr. Ofer Sinai is a founding member of epitaxy group at Israel Center for Advanced Photonics and staff scientist in the solid-state physics device group at Sorek NRC. Dr. Sinai received his PhD from Weizmann Institute of Science for work developing first principle computational methods for semiconductor interface. Question and answer in this webinar will be at the end of the lecture. Please post your questions on the chat tab. I wish you all pleasant and useful listening. Dr. Sinai, the stage is yours.
Thank you very much, Shlomo. I've never done this webinar before, but yeah, it'll be interesting. As Shlomo said, please post your questions. I won't be able to read them while I'm lecturing, but I hope it will be clear enough so that you don't lose track. So I work in the Israel Center for Advanced Photonics. I am in charge of the MBE nitride growth chamber there in the epitaxial growth group. And I'll give you more information about that as we go along. And I want to start with a kind of an overview of, wait a moment. Yeah, kind of an overview of, I mean, I'm sure you're familiar with the idea of history through material. From the Stone Age to the Steel Age, the cutting edge of the technology of the leading civilizations has been a certain material. And from about 1950 or so, people have taken to calling the current age the so-called silicon age. Now, silicon is the basis for advanced technology, the leading edge material, or has been until now. And it's a very attractive material. It's very common. It's made from sand. I'm sure you are familiar with this, or some of you are. It's made from sand. It's undergone decades of optimization, from 1,000 processors on chip 50 years ago to 100 billion processors on a chip 2 years ago, and it has hundreds of billions of dollars of investment. So it's a very, very mature technology. But we are reaching the places where the intrinsic properties of the material may be limiting us in some, at least for some applications. Silicon is an indirect bandgap semiconductor. That implies that its electro-optical efficiency is not very high, and you can't make light sources out of it. In addition, it has a bandgap of only about 1 electron volt, which is very useful for some things, but going to applications that require very high potential, very high voltages or currents, this puts a strong limit on the breakdown field of devices. Devices simply break down under high voltage. So people have begun to ask the question: so what's next? What comes after silicon? What's going to be the leading edge material technology after silicon, which does not imply that silicon is going anywhere. It just means that the cutting edge is going to move on. And there are a lot of answers to this. I'm not going to go over all the answers. I'm going to suggest one of these answers. And that is the gallium nitride family. Now, the gallium nitride is basically, it's also a semiconductor. It is based on nitride, it's a 3-5 semiconductor with a nitrogen as the 5 atom, and gallium and its aluminum and indium as the 3 semiconductor, as the 3 atom, the row 3 atom. It's a direct bandgap semiconductor, which means high optical efficiency. It can have, I mean, the gallium nitride itself, its bandgap is 3.4 electron volts. And if you take the family to the direction of aluminum nitride, then you can get as high as 6 electron volts. So it's a very wide bandgap material, which implies that it can withstand high fields. And if you operate a diode on reverse bias, made from gallium nitride, you get a very low reverse leakage current. Now compare this. Now it's also a family of materials, which means that you can tune properties such as the lattice constant, the bandgap energy, and you'll notice that gallium nitride and in between gallium nitride and indium nitride, we're spanning the entire visible spectrum. And is also a polar material, which means you also have another handle to play with when you're tuning your properties. Compare this to silicon, which is, we've talked about the bandgap and it's a unary crystal. It's made of one kind of atom, so there's no tunability there, and there's no polarization. In addition, gallium nitride is very durable. It's resistant to radiation. It's mechanically hard. It's very chemically stable, and it's also resistant to high temperatures, which is not the case for silicon. Because of this, there are a lot of applications cited for gallium nitride. One of the applications that is already in full force is lighting, of course, because gallium nitride can be a light source. So all of our LED lamps, displays, lasers are coming in and so on. Another application is in high frequency, high power electronics, and in high speed communications, high frequency communications, and in space applications where the durability of gallium nitride and the family is an advantage, for example, in exploration of high temperature environments, such as the face of Venus, where temperature is 500 degrees Celsius normally. So now silicon, this graph it's a graph you see around. It's the horizontal axis is the communication frequency. The vertical axis is the power. And this is about where silicon as far as silicon can go, this semicircle here, quarter of a circle. And all of our applications, our current applications are around here. Now I want you to focus on the lower part, because this is where gallium nitride is really going to make a difference. Gallium nitride could push the envelope almost 2 orders of magnitude further, which means that we can move these applications, which are automotive, low power supplies, and data servers into. We can improve their operation almost tenfold, or even 100-fold. And there are companies already doing this. There's an Israeli company called VISIC, and they're making transistors for automotive, and the gallium nitride transistors, they claim on their website, allow for three times higher power density, 50% less power losses, and an overall lower system cost. And as for low power supplies, Anchors and other companies are all already selling like this small kind of a charger, which is a 65-watt charger. It's enough to, imagine a charger which is big. You'd think of it as a phone charger, but it's actually strong enough to charge your laptop. And that's just the beginning. And over here on the very high end is high-speed communications, 5G and beyond 5G communications. Now, I should also mention that there are other materials, as I said, silicon carbide, for example, it's an indirect bandgap semiconductor, but it's also cited as a useful for other applications that are mentioned here. Now, gallium nitride is on the way. I mean, it's rapidly mature. It's a rapidly maturing industry. It's the killer application that is opened the way is LEDs, light emitting diodes, the lighting market. And that is the main driver for the industry of gallium nitride, an advanced kind of very fast transistor, HEMT transistors. I'll talk about them a bit later, are also coming in, and the production nowadays is based on a MOCVD epitaxy. So I want to talk about what is the method today? So epitaxy is in general the growth of one crystalline material and another such that the crystal directions are aligned. The easiest way to think of it is kind of extending the substrate crystal. You have a crystal, you simply extend it, and you can possibly vary the composition. It's like arranging eggs inside a carton, while the carton is, call it the gallium nitride substrate. Say it's terminated with N atoms, you're now arranging gallium atoms, and you can also play with the composition. You can put in some indium atoms, for example, and you get this is epitaxy of indium gallium nitride on gallium nitride. And the Paul Brode Institute made a very nice kind of simulation of what's going on. You're actually bringing atoms, onto the surface. The atoms are.
No.
Do you see the? I hope you can see the video. You see.
Hello.
And we can see the video.
Yeah. Okay. Somebody is talking. So. Anyway, so you can see the video of this is actually epitaxial growth, where it's a layer by layer growth. Atoms arrive on the surface and arrange themselves into a perfect crystal, ideally, hopefully perfect. And there are different kinds of growth here. So this is basically the idea. Now, specifically metal organic chemical vapor deposition, or MOCVD. In this system, the atoms that you're bringing to the surface are being stabilized by organic ligands, and as they arrive at the surface, the ligands are removed and the atoms remain on the surface. There are a lot of processes going on here. It's part of the tricks of the trade, but this is the principle of MOCVD. I want to tell you more about MBE, or molecular beam epitaxy. Now, in molecular beam epitaxy, the sources are bare atoms. Okay, the atoms are brought to the surface using thermal evaporation of pure materials. It's a form of vapor phase epitaxy. The atoms are, as I say, bare. So they're not stabilized. So in order to keep everything clean, you need to have an ultra high vacuum environment. That means 10 to the minus 10 to the minus 10 to the minus 11 torr to prevent contamination. And you monitor this all the time. The whole chamber is cooled with liquid nitrogen. There are a lot of things going on here. You have fine control of growth conditions, substrate temperature, the rotation. You have fine control of the atom fluxes by heating. And you have a very powerful in situ characterization by shining an electron beam onto the surface at an oblique angle, which gives you an electron diffraction pattern from the surface, which you can actually follow the growth step by step, layer by layer at the atomic level. This is called READ, reflection high energy electron diffraction. And this green image here is an example of READ. This is specifically something that we grew here. It's indium nitride islands on top of gallium nitride. So you can see the islands as dots, and gallium nitride is smooth. Gallium nitride, is the substrate. So comparing MOCVD to MBE, we can see that MBE there are differences. MBE is a bit slower. As I said, it's based on thermal evaporation. What this means that you need elements that have suitable vapor pressure. If you need to introduce something from a gas phase source, such as nitrogen, then you need to dissociate it in some way. As opposed to MOCVD, where the precursors are they impose some restrictions because you need them to dissociate properly on the surface. The materials are often hazardous, so there's also safety considerations here. And yeah, going on. The MOCVD is a chemical deposition system, while MB is a physical deposition system. There are advantages and disadvantages to this. Both methods use heated substrates, but MOCVD, the precursor dissociation is a strong limitation on, or a constraint, shall we say, to the usage. In MB, we have more freedom to choose the substrate temperature to meet the conditions that we need. Because of the temperature and because of the ultra-high vacuum environment and fast shuttering of the beams, MB tends to give much atomically smooth surfaces and much sharper interfaces between layers. And there is, from this paper from 2017, there's an example of aluminium nitride grown on gallium, as sandwiched between gallium nitride, and you can see the interfaces. The same structure grown by MOCVD is very diffused, which is sometimes a problem. MB also has a very low background doping. Because of the organic precursors, you get a lot of, you can't avoid a lot of background doping of the gallium nitride, of the grown gallium nitride with carbon or hydrogen atoms. Particularly for gallium nitride, the P doping in gallium nitride is based on magnesium. And since the MOCVD environment is rich in hydrogen, the magnesium is passivated by the hydrogen. And the Nobel Prize of 2014 was actually for finding a way to get rid of this hydrogen and activating the magnesium. This is not a problem that we have in MBE because there is no hydrogen around, or not much anyway. And as I mentioned, we have atomic level in situ characterization, the read. Now MB also, because it's a closed system, a very clean system, it can produce for months without undergoing maintenance. Maintenance in the MOCVD is a bit more often, but it's a fast maintenance cycle, which gives you a bit more flexibility than MBE in the terms of changing sources and so on. And one example where I wanted to mention where precursors are a real issue is in the production of next generation high electron mobility transistors. These are an advanced kind of transistor that is much faster and much faster switching than regular silicon transistors. It's based on an effective polarization between a gallium nitride and a barrier of aluminium gallium nitride. And this polarization creates a 2D electron gas at the interface. The current state of the art is about 500 ohms per square resistance. If you use an advanced kind of barrier incorporating scandium, aluminium scandium nitride, then you can get to much higher. I mean, there are reports of about 150 ohms per squared, which is almost more than 3 times better. And at the moment, there are no good precursors in MOCVD to do this. In MBE, it's just evaporating the scandium, basically. Now, MBE is there is, and it's already an industrial tool. Also, I mean, it's more mature for 3-5 materials which are not nitrides. And the large producers are already investing in production tools. There is a company called Vico with a machine that can take 3 200mm wafers, and you have their competitor Reber, which makes a machine which can take 4 200mm wafers. And there is a rising interest in MBE for industry in general. This company, Inolum, produces only with MBE. They make gallium arsenide-based layers or diodes. And in recent years, there is also an attempt at an industrial gallium nitride MBE from a Korean company. So we're on the way. And basically, what we're doing in the Israel Center for Advanced Photonics is we're trying to push this ahead. We're doing research and development for the industry, or hopefully eventually for the industry. So this would be the time to introduce the center for those of you who don't know it yet. It is a national center for applied photonics. We have unique infrastructure for specialty optical fibers, which I'm not mentioning today, and for semiconductor design and epitaxy, which is where I am. We have an MBE machine, 2 chambers. We grow nitrides and 3,5s, which are not nitrides. It's the only machine of this kind in Israel, and takes substrates up to a 4-inch. And we also have an MOCVD machine. It's a dual machine. It's a dual growth machine, which can grow nitrides or 3,5 materials with a relatively quick switchover. Again, it's the only MOCVD machine in Israel. Now, what we're focusing on is on industry suitable. What I'm focusing on is on industry suitable gallium nitride growth techniques, and I want to tell you a little bit about these different things. The first thing is interval-based growth. As I'll explain in a moment, this provides improved uniformity despite temperature variations, and it can allow for a fast growth while keeping good, like high-quality crystals. And we've been working on selective growth because MBE is a physical vapor technique, is a physical deposition technique, then that makes it a bit less versatile in the sense of growing in certain growing layers on certain places, but not on others. And we've found solutions for that. And also interrupted growth. This is something we're checking, we're researching, and trying to see if we can grow from day to day, then we can make arbitrarily thick layers despite the growth rate, which is slightly lower than MOCVD. So I'll start with the interval growth. In order to understand why interval growth is useful, the key point to understand is that the surface of the gallium nitride needs to be, in MBE, it needs to be constantly under a layer of two monolayers of gallium. And the wetting by gallium improves the mobility of atoms on the surface immensely, and so improves the crystal quality. And there is this, you can see this diagram of a temperature, the substrate temperature on the horizontal axis, and the flux of gallium. This is actually taking a constant flux of nitrogen atoms. The increase of the flux of the gallium actually means that there's more gallium per nitrogen. The gallium also evaporates from the surface, and in between, as you increase the flux of the gallium, you're moving from the so-called N-stable regime, where the mobility is low and you get poor quality and roughening of the surface, into the intermediate regimes, where you get a higher quality of surface and higher quality of crystal, intermediate gallium stable. And finally, as you go to higher fluxes of gallium, more gallium per nitrogen atom coming in, then you get so-called droplet regimes, which can cause can deteriorate the crystal quality. And the deterioration of crystal quality means, let's say that means dislocations, places where where devices may fail or lasers may fail, where it may not work, non-radiative pathways, and so on. So we aim for high quality crystals, which means we're aiming for the border here between the intermediate gallium stable and the droplet regime. That is the best region to grow in. Problem is that it's a very fine balance to strike, and I should say we can monitor this again with the read. These are all images of read. You can see that they're different from each other as you move between regimes. So you can see this in situ while you're growing. You can adjust if necessary. But what it means, because we're aiming for such a fine balance between gallium and nitrogen fluxes, then if the temperature is slightly higher and gallium evaporates more from the surface, that may shift us away from the regime, which creates some trouble. If there's even small temperature fluctuations, then this can cause us some trouble. So the solution is to shuttle between regimes. And that means, say, for example, you're growing at 600 degrees substrate temperature, then you flood the surface with a certain amount of gallium, and then you eliminate those droplets periodically. Then these can be very very fast cycles or slower cycles, depending on the relation between gallium coming in, gallium and nitrogen fluxes. And there's a zoo of different techniques here. You can flow the metal and the nitrogen together and then stop them both. This has a name, it's called migration enhanced epitaxy. You can only stop the metal. I mean, you can continually flow the nitrogen and stop metal, and then add metal, stop metal, add metal. That's called metal modulated epitaxy. And there is a variety of techniques. I call them all interval epitaxy or pulsed growth sometimes. And these kinds of techniques have a lot of advantage for especially indium gallium nitride. The whole range of alloys between gallium nitride and indium nitride is accessible using these kinds of pulsed growth techniques. And because of differences in how well the atoms are incorporated, you need to use this kind of technique in order to achieve good single phase alloys. And it also has advantages for making quantum wells, some superlattices. That means repeated cycles of different material, of two different compositions, one after the other. And you can even get to self-assembled superlattices if you play with it correctly. There's also been reports in the literature for that. Here in the center, we've worked on, for example, this is an example of growing single-phase indium gallium nitride. As I showed you, you can monitor the cycle in situ using the read, the electron diffraction, and pyrometry. The cycle here is a cycle where the nitrogen and the gallium are flowed continuously, and the indium is intervaled, or it's flowed at intervals. And when we are growing in this technique, and then taking it to high resolution, using our high resolution XRD or X-ray diffraction to analyze the structure, we see that there is no segregation. I mean, we don't get. Sometimes you can get indium nitride segregated from the indium gallium nitride or from gallium nitride. Here, we won't go into what these measurements are, but the gallium nitride has a peak here. The indium gallium nitride is a peak here. In this case, it's a higher percentage. So it's a signal here, and here you have a signal of indium gallium nitride, 40% indium, and no other signals. So, and this means that what we've grown is pure phase indium gallium nitride. Right, and another example, as I said, this technique is also, it's convenient for quantum wells. In this case, I've grown a sharp interface indium gallium nitride quantum wells. And the idea here is that, well, these are the, well, up is open and down is shut. So you see that the indium is run at intervals, the nitrogen is run at intervals. The interval kind of technique is, as I said, there's a variety. And the fluxes are arranged such that indium is incorporated within the quantum well. It's excluded in the quantum barrier, so you get pure gallium nitride in the quantum barrier. And there is a slight excess of metal throughout the growth. And again, the surface conditions are monitored in situ. You see this is the read trace, and this is the pyrometer apparent temperature. Okay, this is also affected by what's going on at the surface. And you can see that, first of all, that they repeat themselves as cycles go along. This cycle is the cycle in which the indium gallium nitride quantum barrier grows. This cycle is this is the well, this is the barrier. And you can even see, if you see this in the read, there is a brightening and a darkening and a brightening again. And this is, I mentioned this once, I mean, the wetting of the surface that we hope for is actually two monolayers, and what we're seeing here is actually the monolayer, the first monolayer desorbing, and then the second monolayer desorbing, so you get a very, very fine control of what's going on. And when take it later to the X-ray diffraction analysis, you can see that the multiple quantum well structure measurement matches the model very precisely, which is what we expected. We also took these samples to HRTEM, collaboration with the Technion, and you can see with elemental analysis, you can see that the indium contrast, I mean, you get indium inside the quantum wells, not outside the quantum wells. The interfaces are at the level of atoms, single atoms, between the quantum wells and the quantum barriers, and we have good compositional control. So this is a good result. So much for interval epitaxy for now. As I mentioned, MBE is a physical vapor deposition technique, so selectivity is a challenge, or was a challenge. What we did, we were able to selectively grow epitaxial gallium nitride using a growth mask. And as you can see, this is the mask over here, it's a hard mask. Here we've grown selectively epitaxial gallium nitride. When the mask is removed, you can see the substrate, you can see the epitaxial GaN in the microscope. You can even see this in the microscope. This is, I believe, Nomarsky. And this is actually well, it's selective growth, as you can see. Finally, I wanted to tell you a little bit about us. These are really experiments just now where we've been growing in interrupted growth of gallium nitride. As I said, gallium nitride tends to be a bit slower than MOCVD. So in this case, we grew 2 microns of undoped gallium nitride. And the question is, and in one case, we grew the 2 microns in one go, and then second case, we grew first about 2/3 of the layer, and then the last third in another day. In between, they actually moved the wafer out of the growth chamber and brought it back. And the question we're asking is, does the interruption change the growth quality? So during the growth, analyzing the brightness of the read intensity, you can see that at the top you have the cycles of the interrupted, the uninterrupted. I say cycles. What I mean is we're using interval growth here. At the top, you can see the cycles of growth of the uninterrupted run. And at the bottom, you can see the cycles of the growth of the interrupted run after the interruption. I mean, after the wafer has been grown, taken out, brought back, and the growth has resumed. And it basically, these traces are very similar. You can even see, if you look carefully, you can see drop, rise, and drop, which is exactly the same 2 monolayer dynamic that I showed you before in the when I introduced the interval growth epitaxy of indium gallium nitride. And you can see this also here. So all in all, in situ, we don't see many differences, and it looks the same. So far, we've had time to examine also the surface of the growth. The large scale, you can see this is a Nomarsky image. There are dunes. You can see these kinds of dunes. It's like a desert. These dunes are they're coming from the substrate, actually, that on which we grew, which is a gallium nitride template. It was grown a gallium nitride substrate. You can see that the images are rather similar, slight differences in hue, but they are basically similar. And looking at the highest magnification we have, you can see that the small scale, micron scale features of the surface are practically identical. So we see minor differences here, and we're working on characterizing this material further. We're also trying to leverage other advantages of molecular beam epitaxy. As I said, there's a low background, so we've managed already to grow gallium nitride with a very low background doping under 10 to the power of 15 per cubic centimeter. I'm talking about the gallium nitride is naturally N-type, so this is an N-type growth with high mobility. And we've also done a lot of work on contacts to N-type gallium nitride, specifically HEMTs, with very, very low resistivity. And this is important for high electron mobility transistors because they need to run very fast and they need good contacts. And we managed to achieve very high doping uniformly across the wafer, as you can see here. And this is something that you need to do in MBE because you don't want to destroy it's a regrowth on top of a structure that has already been grown. And if you do this at high temperature, you can destroy the structure that you've grown, destroy the interfaces. So this is also something that we've achieved. As you can see, the resistance of these contacts is extremely low, 0.015 ohm per millimeter, which is very, very low. This is the resistance of the metal gallium nitride contact here is even lower than that. It's about half of that. So to summarize, I hope I've convinced you that gallium nitride offers some advantages over common semiconductors for some applications. High frequency, high power electronic applications, things happening in harsh environments, and where you need light sources, in particular ultraviolet light sources, because you can push the nitride family to the deep ultraviolet using alloying with aluminium. Molecular beam epitaxy is a very promising technique. It's a cutting edge growth method. It gives sharp interfaces. I've mentioned that you can do p-type doping, that when you dope with magnesium, you don't need to remove the hydrogen from your growth because there is no hydrogen in your growth. But the meaning of this is that you can grow p-type layers, buried p-type layers, which is something that is necessary for tunnel junctions, etc. I've shown you that you can grow. I've shown you work on advanced high electron mobility transistors or HEMTs using scandium and very low resistance contacts. And as I've said, the work in ICAP's 3 nitride MBE focuses on these industry suitable techniques. That's interval growth, I've shown you, selective growth, and interrupted growth. And I'm happy to answer questions.
Okay, it's time for questions, so please don't hesitate.
I think you should see the chat. No chat yet.
I have a question for you. What is your short-term goals and the long-term goals concerning the MBE?
You'll need to be more specific. But the work in the center is project-based. Our long-term goals are to be the go-to the go-to center when you need to develop a new kind of device or a new kind of application for your, based on 3-5 materials, particularly in my case, gallium nitride. That would be the long-term goal. The short-term goals are based on the projects. I mean, taking what I've shown you here, I'm currently working on choosing and perfecting the correct interval-based kind of growth that will give us a very high quality gallium nitride crystals, that's like that, and effective p-type doping and so on. We're working on diodes now.
Okay. I see that in the chat you have you have a question.
Okay. Well, the question is, are you using Raman spectroscopy to characterize the layers? The answer is no. Raman spectroscopy is not usually used to characterize nitrides. So the answer is generally no.
Is this MBE process is used in the industry, in the high volume industry?
Well, as I said, the MBE, we know of several companies who I've shown you Inalum in one of the previous slides. They grow, they use gallium, they use MBE to grow gallium arsenide. I know of another company, a very successful company, which also uses MBE as an industrial, in an industrial setting. It's a very successful company, as I say. And in the nitrides, not yet. In the nitrides, there is one company who's taken up the challenge of growing industrial grade gallium nitride using MBE, but it's the only one I know as of now. Well, yeah, you have also, there are also suppliers of wafers. Yeah, I mean, there is some adjustment, but high volume, really high volume. I think the company I mentioned, they're just ramping up. Is the main thing.
Eli Weiss ask you a question. You can see it on the chat.
Graphs on slide 28. The question is, can you explain again the two graphs on slide 28? Yes. So these are time. It's actually we're following the brightness of the read. This is on the left here is the read pattern. The brightness of you can see the spots here there are defined spots here, and you take the average brightness of those spots, and the brightness oscillates as the growth proceeds. So when the surface gets covered with the gallium layer, then the brightness drops. When in the interval step, when the gallium evaporates or is incorporated, then the pattern brightens, and so on.
Okay. Is there any more questions? If not, I would like to thank Dr. Ofer Sinai for a very nice presentation. Most of it was new to me, so I was enjoyed very much. So thank you very much, and I hope to see you with some other webinar.
Thanks for the opportunity.
Okay. Thank you.